Thank you. So we are BioNavis company based in Finland. We have Finnish, Italian and Japanese ownership, and our core business is MPSPR. We have been established in 2006, but before that we have been already for 20 years. The technology has been developed in VTT, which has been just presented by Dr. Janusz Sadowski. And since 2006 we have developed the first product, which is SPR Navi 200, which is open and modular instrument. And in 2011, last year, we brought a fully automated machine into the market. And now, what does it do? So, what we do is based on surface plasmon resonance, which is a technology used for 20 years in development of pharma drugs. And so far it has been used only for pharma. They have been following only a very small area of the SPR because of the limitations of the technology. So we thought, here is a nice technology, and at VTT it started so that they wanted to use it for measuring of new materials. So they decided we need something else than what is now there, and they came up with this new setup which is able to measure whole curve of SPR, or surface plasmon resonance. This way we have much more information about what's going on the surface, and we are able not only to probe molecular interactions but also material properties such as thickness and refractive index. So here is the basic principle of SPR. So what we see is molecular interactions. We see the molecules attaching on the surface, and at the same time we see the shift of the SPR curve, and we can see that based on that we can say how much molecules have attached, how fast, and this is essential for a number of chemical new chemicals, new drugs, new materials. But apart from molecular interactions, we can measure also the thickness, and this is the new area where we are entering. No other SPR instrument is really able to probe this. And what we can measure is not only the thickness, but we can measure also when it's being built up. In this case, we are using sensors which they have a metal layer on top of them, which is necessary for the surface plasmon resonance to appear. But then on top of that we can use metals, polymers, semiconductors, biological samples. The main difference in why we can do what others cannot is in the optics. So again, thanks to VTT and their know-how, we have shifted away from lasers with expanding and focusing optics and working at fixed angle, and we have put both the sensor and the laser on moving arms, and this way we are able to cover 40 degrees, which means we are able to work with a number of materials others cannot. So where we can apply it? So when we are looking at the molecular interactions, areas where our clients are using our instrument is nanotechnology. They are looking at nanoparticles, how do they attach or off rates from the surface. They are looking at LB films, Langmuir-Blodgett, at self-assembled monolayers, how they are formed, how thick they are, what is their optical properties. We are looking at functional coatings, and especially biofunctional coatings. We are looking at solar applications. Again, we can look at efficiency, not only at the thickness of the films and how they are formed. We are looking at biomaterials. For instance, for drug, it is important that the drugs are very slowly going into the body. So we look at cellulose as one of the encapsulation materials, or polymers. We are looking at new materials. We can look at corrosion studies, thanks to combining SPR with electrochemistry. We can look at quality control. So overall, this system is very versatile. On one hand, you can measure biological or chemical mechanisms, and on the other hand, you can check then afterwards what is the result, what is the thickness. Based on that, we are able to say whether the molecules are arranged or whether they are collapsed on the surface, and many other things which are not possible with current technologies. So when we look at some of the questions that can be solved is, for instance, affinity or on-off rates of molecules. We can look at the amount of protein in certain sample. This is one of the reasons why one of our clients is also Heineken. We are looking at food processing. We are looking at, here we can see different two materials and how much protein is adsorbed on surface. When you look at it the other way, so when somebody develops a new coating which is preventing attachment, for instance, for food processing, you don't want anything to stay in the tubes which are carrying milk. You don't want any bacteria to grow there. So we can test that and see how well it is effective before going to big scale. Here is an example with DNA, where we have different concentrations of DNA being injected, and again we can follow exactly what's going on, and this is then enabling people to develop new biosensors, again, which can be used for point-of-care diagnostics, or they can be used for agriculture to check for pesticides or toxins. This is the electrochemistry cell which we can use together with SPR. Again, this is useful especially if you are interested also looking at cyclic voltammetry at the same time while you measure SPR. And we are very well working also with small molecules, which is a challenge for many other techniques. We have picomolar sensitivity, but we are also able, with a special label, we are able to get to attomolar sensitivity, which is again unprecedented for systems like this. For material science, again, as I was saying, what we can look at is buildup of material. We can look at depletion. We are looking at the thickness and optical properties. And here is an example when Langmuir blotchet films are formed, and at each we are able to measure the thickness of the layer. So you are able to directly say that one layer will be 2.3 nanometers thick. If we form 10, you can again measure exactly what is the final thickness. No guessing. This is example with metal organic framework, similar study where we are building step by step new layers, and we are then able to measure the thickness of the formed layers. And again, here not only the thickness but also inside. So again, for polymers, this is an important information. Here is an example with graphene. We have been measuring graphene as one of the materials. And here is one of the recent studies which we did for one of our clients. So today heard about ALD, where we are looking at the molecular level deposition or formation of layers. This is made with sputtering. And as you can see, we have confirmed the difference in different parts of the chamber. The thickness have been varying more than 10 nanometers. So this is again for processes where you want to have uniform thickness. This is a way how to optimize. So just as one final example is biosensor group is developing a biosensor for security applications where they are sensing cocaine in this case. And here our sensors are used to really measure how much of the functional material, how should it be formed so that it has maximum specificity for cocaine. So these are the two instruments which we develop and build in Finland. We have 40 instruments around the world. Majority of them are in China and Japan, but we have also many in Europe and USA. In this year we are going to have some installations also in Australia, which we are very happy about, and we are hoping to enter also the Russian market because we see that there is a lot of top chemists in here and engineers, and we see that there is big potential for these instruments here. So all in all, what we can measure is layers from something like few hundred angstroms to 100 nanometers, and then from 350 nanometers to a few microns. And with auto configuration we can go also beyond that to several tens of microns. We can work with metals, semiconductors, and dielectrics, so we are not limited to metals only. And we provide ourselves a range of sensors, but also any processing process that you have, whether it's LB or whether it's ALD, you can use that, and then we can measure with SPR. We have also our own software for analysis of the measurements, both for thickness and for the interactions. And unlike other methods, this is one significant difference to other methods, is also that we are not able only to measure the thickness, but also measure the refractive index at the same time. So you don't have to rely on the values which have been posted from different sources, but you can actually measure the refractive index of your particular material. So all in all, for life sciences, we are looking at picomolar sensitivity measurements. We can combine it with electrochemistry. We are able to measure at 4 milliseconds rates, so very fast measurements. We are able to look at sandwich structures, multiple bindings. We are able to work with nanoparticles and on a number of surfaces which normal SPR cannot do. For material sciences, most important is that we are able to resolve thickness and refractive index at the same time, because we work with multiple wavelengths. We're able to measure in gas and liquid, and we are able to work with a number of materials, as can be seen here: alumina, titanium dioxide, copper, and so on. So this is all from me. We have a distributor in Russia, one in St. Petersburg and one in Moscow, and we are hoping that you will find interest and you will contact me or one of our distributors to get to know more about this technology. Thank you for your attention.